Okay. So 7-2, number 18. All right. 7-2 is the one with p hat. So finding the percentage, confidence interval for that. So 18 gives you something straight up, no words to it. Just get right to the point. It just wants you to find the margin of error. So 7-3 was this here, and 7-4 was this here. I mean 7-2. Sorry. So those are the two that we've talked about so far, and I tried to show you how this basically comes from this type of idea for binomial, trying to set up a confidence interval for a binomial n p hat, so forth. I tried to show you where it came from. In this case, for 7-2, that's where we are now. Where's the error? What piece of this is the error?
Z square root P.
This piece here, right? Because this is p hat, give or take some amount that I'm off by. And the book actually puts it as p hat plus or minus e. Just kind of really make it clear that that's the error piece. That's how much I think I'm off by, give or take that much. So they want you to find, for this problem, number 18, they want you to find this error. So now that you identified what the formula is for what they're asking for, you can start figuring out how to get what you need to plug in there. So how do I get p hat from the situation they gave me? What do you think? What does that x represent? Who remembers that from? Exactly. If you remember from binomial probabilities, x was the number of successes. So if I gave you a whole situation, I say I talked to 80 people and 7 of them said that they watch the show with Nick Lachey nowadays. I saw it in the gym. I was like, Nick Lachey's on a show right now. So 7 out of 80. 7 successes divided by 80 people, right? So if you remember from binomial, x represented successes. So here they tell me directly, they tell me x is something, 220. And n was 500. So then p hat, like Sarah said, p hat's got to be x divided by n. Just make that percentage. 220 successes out of 500 things, right? And of course, if you do that, you should get 44%. 0.44. How's that going? Is that all right? Okay. So you get 0.44. So what's q hat got to be?
0.56.
Yeah, 1 minus that, 0.56. Cool, the rest of it, right? So now I have p hat, I have q hat, I had n from the beginning. The only thing I'm missing still is z. And what do they tell me that helps me get z? Where's that z-score come from? Yeah, I want to be 99% confident. So the z-score tells me, well, how far I have to go out to catch 99% of the stuff. So then I'm 99% sure that that thing catches the real percentage. Right? So the z-score was going to come from 99% confidence. What's the z-score for that? 2.575. And don't be freaked out. It's a good thing. Hopefully you'll start to just remember some of these numbers. Right? People sometimes get a little freaked out. They're like, how the hell did I know 90 is 1.645? Because you do it enough, it kind of sticks in your head. You see a lot of the same z-scores over and over and over. 2575.
How did you get Q hat?
This is overly dramatic. Huh?
How did you get Q hat?
Anytime I know P and Q, they have to add to 1. So if I know P and know Q, I don't care if they're wearing hats or not. They have to still act the same way. So P sock plus Q sock. There is no P sock, by the way. It would still equal 1, whatever P and Q are. So now it's just plug and chug, right? Now to get your error, it's going to be this many steps away. This many steps away, right? So that many of these. These are now my standard deviations for p-hat situations. That's my z-score times my standard deviation. So now just throw that in there. You've got to be a little careful how you put in the calculator. I think we did that last time. Some of you guys with the brand new TIs, the square root bar gets bigger, which is nice. Some of us with the old one, it just opens up a stupid parenthesis. Just don't close that parenthesis till you get everything in there. So you would put in there 0.44 times 0.56 divided by 500. Close parenthesis there at the end. Get used to trying to put it all in there at once. You don't want to have to keep on carrying 8 decimal places with you as you go. That kind of sucks a lot. So don't do that. Let's make sure we can all get the same answer from this. Go ahead and try to do that. Yeah, I get 0.0572 if you want to go out there. Right? Does everybody get that same thing? 0.0572? Now is a really good time to let me know you don't. Okay. Oh, you divided by it's times. Right? It's z times that. Yeah, that's all. I hit enter. You'd be good. There you go. Sweet. Alright, so I'm assuming everybody else is alright. Now, chapter 7, compared to some of what we've already done, chapter 7 is normally a very concrete section. It's like you can get the image in your head. If I just catch this much stuff, I'm obviously that sure I taught the right thing. The formulas are very plug-and-chuggish, which I never try to teach it that way, but once you've gone through the concept, you're like, well, I'll just plug the right stuff in the right place and get what I need. It's kind of nice. You can really sink your teeth into this stuff, right? Hopefully at the same time you remember the concept, but at least you can get the numbers going right. So what does this really mean then? By itself, what does this tell me?
Amount of error.
The amount of error. So it looks like I'm off by almost
5%. 6%.
almost 6%, right? I'm almost off by 6% if I want to be 99% sure. So why did it come out to such a huge percentage? It's normally like 3 or 4. Can somebody point out a couple things as to why this might have come out so big? How big is my confidence interval? How big do I want it to be? Pretty damn big, right? So of course it's going to be a little bigger than it would have because I want to be 99% sure. Holy shit, I got to go way the hell out there to be 99% sure. My sample is actually, it seems like a decent size, but normally for these you see in the thousands or the 2000s or so. So the sample relatively is smaller. So if you go to Gallup, I think I've shown you Gallup.com a couple times. At the bottom, their samples are almost always at least 1,200, if not up to 2,000. That's why they almost always have plus or minus 3, plus or minus 4 percentage points. Because if you make the sample bigger, obviously your error should go down. Because then you're more sure about what you're seeing. It's really kick-ass cool to see that in the formula. Math agrees with what makes sense. Wow. Sometimes that happens. All the time, but right now I'll say sometimes. Yeah.
So with that section, we stop once we find the error, but on 22, 23, we take that error and then add or subtract.
I like it. So if this was a problem from later, you would actually take the p-hat plus or minus the error we found. You would take the, what was p-hat, 0.44, give or take the 0.057. So be careful with what they ask for. I mean, if you do more than they ask for, that's fine. Doing less is bad. But really, all they wanted here was the error. If you get into the flow of things, and you just keep making confidence intervals anywhere, you found the error. That's fine. You just went further than you had to. But all they wanted there was that. And later, they went the whole confidence interval. And they don't really ask you for a statement. But if I were you, I would write it anyway, so that when I go to grade it, I can tell you if something's wrong with your statement, right? Because I'm going to ask for a conclusion on a quiz or a test, right? So you have to be able to write that out. So how would I write that out? Well, we didn't really do this here, but this would be, just make this 6 for easiness. It'd be 38 to 50, right? So how would we write the conclusion here?
We are 99%.
We are 99% confident that.
Interval.
Yeah, so you got to be a little careful with the semantics. The interval 0.38 to 0.50, or even 38 to 50%. Contains the true percentage of the population. Now in this case, they didn't really tell me what it was a percentage of, right? They didn't say 220 what's out of 500. You should put physically what's going on here, right? So if it was 220 people out of 500 that plan to vote in the next election, then you say the true percentage of all people who plan to vote in the next election.
Say that again, please.
So if this would have been, they didn't really tell me physically what these were, did they? They just gave me numbers. If this was, will you vote? And 220 people said yes, then this would be, we are 99% confident that the interval 38% to 50% contains the true percentage of all people who will vote in the next election. You make it specific to the problem, right? What physically is going on.
I'm having a problem with the first half because I don't understand how you got 38 to 50.
Oh, one thing is I rounded that off, right, just to make it quick to get some numbers.
Yeah.
But what does this tell you to do? Take 0.44 minus 0.06 and 0.44 plus 0.06. That's all. Plus or minus means do both. And the easiest place I can point you to is quadratic formula. You remember that stuff?
Yeah. So that's how you would do like 9, let's say like 11. It's just doing that, right?
11 is kind of going backwards. And the reason they gave us problems like number 11 is because very often you'll see confidence intervals given in that format. So they're saying if you see that, as a stats student, you better know what the hell that means. So if I did see 0.437 to 0.529, can anybody tell me how would I find p hat? This is a confidence interval for percentage.
Add them and divide by 2.
Yeah, because p hat has to be where? It's got to be right in the middle. Yeah, so add them together, divide by 2, and you get something. 966, so 483 things. So p hat's got to be right in the middle, 0.483. And then what's the error got to be?
The upper minus the lower divided by 2.
That or just how far away that is from either side, right? The whole thing is twice the error, cool? Because the error is just take the mean or the p hat, go up this much or down this much. So me, I always kind of do this. I say, well, that's 46 away from that.
Mm-hmm.
So it'll be 0.046, almost 5% error. Did you guys see that? Or you subtract these two and divide by 2, because that would be twice as big as the error. The error should only go from the middle up one way or down, not both. You guys really like this, I can tell. This step here is really kind of silly. If I give you two numbers and I say, what I'm really saying is, here are these two numbers. Right, here's two numbers. Can you tell me what number's in the middle? And can you tell me how far the middle is away from either side? That's the question. Because the number in the middle is p hat or x bar. So now I can put it into statistics. I could give this to my algebra students and not feel bad about it because they should be able to do this math, right? I wouldn't say p hat and error. I would say what number's in the middle. Okay, take the average. And how far is that number in the middle away from either side? Take the difference, right? That's all you got to do. You guys with me a little bit? Tiny bit? Because again, the confidence interval, what's got to be right in the middle? P hat or x bar. Because how do you make the sides? Don't you find p hat or x bar and then add and subtract the same damn thing to it? Mm-hmm. So shouldn't the middle be the freaking p hat or x bar? So if they give me a confidence interval that's already been made, what must the p hat or x bar have been? The thing that's in the freaking middle, right? So you just add them up, divide by 2, take the average. And what's the error? The error is defined to be how far away the sides are from the middle. This is the error here, this is the error there. That's why if you wanted to, you could subtract these two and divide by 2, because how far apart is one side from the other side? 2 errors, right? So on one level, that's just, can you add, subtract, multiply, divide correctly to get this number, right? That's not even statistics right there. That's just play with these numbers. Okay, maybe. Let me give you something along the same lines there. Has everybody got this here? Here's really what confidence intervals are good for. If there was a claim at a school that the females scored higher than the males in some standardized test, right? The women all got together and said, "You guys suck. We did better than you." Ha! And then they took a sample, and they got these two confidence intervals for the scores on the test. The females, this confidence interval for the females, let's say was this, and for the males was that. I don't even need to point it. I'm not sure why I did that, but 81%, 92%, 74%, 82%. Do these confidence intervals support the claim that the females definitely scored higher than the men? Why not?
Because not as confident about
82.
themselves.
Is there a chance that they scored the same thing according to your confidence intervals?
Yes.
Yes, they could have, because they overlap, right? They overlap. So there's a chance they could be the same. So what would be evidence that they were females scored higher than the men? If this was 0.83, then according to your confidence intervals, could they be the same thing? No. What are the chances you're wrong? Well, if this is 99% confidence interval, there's a 1% chance I'm wrong, right? And that's normally a chance I can live with. So if somebody shows me evidence, and I'm 1% sure that I'm wrong, I'm 99% sure I'm right, this evidence shows this, I'm like, well, shit, I'm going to say, yeah, that's what it is, right? Still a chance you're wrong, like always. Do you guys see that? You're going to see some problems in the book like that. In the book, they normally do, they claim that they scored 94%, and the confidence interval was this. Is there any chance their claim is right according to your confidence interval? No. It can't be. According to your confidence interval, the highest it could be is 92%. That's the kind of question you'll see more often in the book. But what happens in real life is you take two different populations, make a confidence interval for both, and if they overlap, they could be the same. If they don't, they can't. Understanding in the background, there's always that chance you're wrong, which is one reason why people hate stats, but to me, stats is the most honest math course there is. I might be wrong, shit. Right?
So these don't overlap, so.
These do overlap, don't they? Females start at 0.81.
Oh, yeah.
Here's the females, and males start at 0.82. I mean, end at 0.82. So they do overlap a little bit. So it's possible that the females averaged in 81 and the males averaged in 82. Isn't that true? So isn't it possible a male scored higher than the females? Or at least as well, right? So then the claim is not backed up by this. Do you see that? And that's really where we're headed, is how to investigate somebody's claim about something. If you make a claim, how do you show it's true or disprove it? You go collect data and look at the data. Just watch Mythbusters. I love that show. They do exactly that. They make a claim, they try to collect data, and they see if it matches what they thought would happen.
So real quick, can you repeat, what's the question they would ask with that?
They would
With the
say,
81
is it
and
possible, does this evidence support that the females scored higher than the males? No, it does not support that, because it allows for them scoring the same thing. It even allows for the men scoring higher than the women, doesn't it? So a similar one would be, this guy's got 44% of the voters saying this guy's got 42%. Is he definitely going to win? A couple things wrong with that statement. You know, like, for example, they didn't talk to me. They never call me. Never get those phone calls. But at the bottom, you see this plus or minus 4 percentage points. So candidate A, candidate B, A's leading according to this, but what could be happening? If it's off by 4%, he could be at 46 and he could be at 40. He could be way ahead of him. And that's what I hate about these stupid polls. They show this shit. They show this at the bottom. Nobody understands what the hell that means. He's going to win. I want B to win. I'm not going to go vote. Well, then you just ensured that this is going to happen. Good job. Right? They should stop publishing this shit because people don't understand it well enough to know what this means. I have strong feelings. So any other questions from you? Yeah.
26 from
7,
2.
2. Oh, okay. This is the last thing I had to do in this section. I don't think I had done this one yet. Remember how we got a formula for figuring out how big a sample had to be to do something? You guys remember that? You think to yourself, was I here that day? But there's that one formula for means that looks like this. Does that seem vaguely familiar? So all we did was you took the error equals that piece of it, and we solved for n. So we can do the same thing with this. This is the error. So I'm not going to use this. I might as well. Sleep. So this is the error. So I can say error equals this piece. Let me guide you through the algebra a little bit. How do I solve for n? What maybe can I do first that will make this a little easier?
Square both sides?
Square both sides, because the n is, not only is it stuck underneath, it's stuck under a square root. That kind of sucks. So the whole thing about algebra is freeing up your variable where it is, getting it unstuck. So square both sides. Get e squared equals z squared. And all this just gets freed up, right? How we doing? Now here's the cool shortcut I mentioned the other day. To solve for n, you just take this and switch it. Pop. Multiply the n up, divide the e squared down, they just effectively switch. That's a really good shortcut to know. So n equals z squared, p hat q hat over e squared. So that's your equivalent formula for finding how large a sample has to be within certain percentage points of the true percentage. So this one is for to be within so much of the mean, because there's no p's in it. This one's for being within a certain percentage of the population, because there's p's in it. It's really easy to tell which one to use when.
Say it one more time.
This one is definitely for if they ask you how large of a sample do you have to take to be within 1 inch of the real mean, right? Not percentage. I don't want to use the one percentages in it then. I want to use this guy, right? This would be if they say how large of a sample do you have to take to be within 5% of the true percentage of people who are going to vote for candidate B. That'd be this guy because they want to talk about percentages then, right? Let me ask you kind of a funky question. What if you don't know what the hell P hat and Q hat are? You haven't taken a sample yet, have you? The question is, how large of a sample do you have to take? So if you don't know what P hat and Q hat are, what are your best guess? What's your best guess? 50-50. Does that make sense so far? So in some of these problems, they're going to say P hat and Q hat are unknown. Then you just put in there 0.5 and 0.5. And what is 0.5 times 0.5? So if you notice, which is 0.25. And in the book, if you look at the formula, they actually have a formula that says z squared 0.25 over e squared. That's where the hell they got the 0.25 from. Putting your best guess in. What's your best guess when you don't know a percentage? 50-50. Mathematically, that makes n bigger than it would have to be. If you made it 49-51, n would be a little smaller. So let me ask you this. If you don't know something that you really kind of should know, should your sample get larger or smaller to cover that fact that you don't know something?
Larger.
Bigger. So it only makes sense. 50-50 because I don't know. N then is the biggest it can be to cover for your not knowing. Maybe. So just to show you what it sounds like in the book, like I'm sorry, which one was I actually talking about?
26. Oh, 26?
There you go. Margin of error 0.005. confidence level 99%. P hat and Q hat are unknown. There you go. So when you don't know P hat and Q hat, you put 0.5, 0.5 in for both, right? Because that's your best guess, 50-50. So for example, I asked you the classroom at the end, what percentage in there are men? I don't have a freaking clue. So what's your best guess? Half of them. What the hell, right? You guys kind of with me on that? That's why that's the way it is.
Could you walk through and do 26?
Sure. So 26 says, how large of a sample do you have to take in this situation, right? Sample size required. So they want to be off by 0.5%, right? They want to get really close. So the sample's probably going to be large to do that, right? You're going to have to take a big-ass sample to be that close. What else did they tell me? Confidence level is 99%, which tells me what? Z is 2575. Cool. That's what I think we're all going to have possibly memorized. We've seen that a lot already. So, N equals Z squared P hat Q hat over E squared. I got everything I need. Z is 2.575. Square that bad boy. What's P hat? 0.5. So 0.5. Q hat then must be 0.5. Over the error squared. The biggest mistake I see is if they say you want to be within 2%, for example, what is E then? If I want to be within 2%, what's E? E is not 2, E is 0.02. Exactly. Otherwise, you come up with sample sizes of like 0.5. You need half a person. No, something went wrong. Right? So make those percentages before you plug them into a formula. You make them into decimals, of course. So whatever the hell this comes out to be. Yeah, wow. Hundreds. So I'm thinking it's like 1, 2, 1, 2, 60,000 or something. 66.
306.25.
So what's the real answer?
307.
307, 11. So that goes along with what we thought. If they want to be really close to the right answer, well, then you're going to have to take a damn big sample, aren't you? Because the larger the sample, the less uncertainty, the more sure you are. If you want to be really sure, you need a really big sample. 66,000 people. You won't see that on Gallup, I promise you. We talked to 66,000 people? No, you didn't. Okay, don't want that job. I want 66,000 people. No. Okay, all right. So how are we doing so far? Is that semi-decent? All right, a little bit. I love the looks of pain I get off of some of you guys sometimes. It's like, all right. This next section is a lot. Oh, sorry. What's up?
Just about what you were saying about the error, make sure it's a percentage. If it says within 3 points of the population.
Within 3 percentage points?
That's what I'm not I don't know.
So that's 3%. So then you got to make it 0.03. Yeah.
Okay.
Yeah. Cool. All right. Now, I'm hoping this next section, and just to give you a little background to this, this is what we're about to learn is called the student's T distribution, and it's because the guy who came up with it worked at Guinness Brewery, and he was trying to do some analysis on something, and he wasn't really supposed to be doing it, so he used alias. He called himself Student when he did this work, so that's why it's called Student T. I always like to point this out in case anybody likes Guinness. They seem to maybe have more of a connection with statistics that actually fed into this construction of this thing. And what he's trying to do What's kind of weird about this formula, besides the whole damn thing? Hopefully that's not the answer. What's kind of weird about that? We're admitting what used to go here. Remember where this came from? We have to use a sample mean because we don't know the
Population.
And of course that makes sense. We're going to take a sample. We don't know what the population mean is. I haven't talked to everybody in the world. I just want to take a sample. So what is a remnant in here that still doesn't make sense?
Standard deviation.
Yeah, why in the world would you not know the population mean, but somehow you know the population standard deviation? That's a neat trick. Right? Now the reason we did this is just to get into this. Just to get used. And sometimes you do, actually. Sometimes you do. And how would you know this? If you had all the SAT scores, and you know how they're all distributed, but then you took a sample of those, maybe just the women, or maybe just a certain ethnic group, you would still know the population standard deviation, right? Mm-hmm. But you'd have to calculate their sample mean. So this doesn't not exist in nature anywhere. This formula is used. Just what's more likely to happen is I don't know either thing, the population mean or the population standard deviation, right? Now tell me what should happen. If I get a confidence interval from this, let's say I do some work and I get like 4.1 to 5.8 is my confidence interval, let's say. What should happen to my confidence interval if I say, oh crap, I used the sample standard deviation here. I didn't know what this real standard deviation was. How will I cover my ass for that fact?
Make it larger.
Make it larger, right? Somehow make it larger. You just don't arbitrarily go, oh, I want it, let's make it 3.9 to 6.1. Yeah, there you go. No. There's actually a very prescribed way to do it. If I took a sample of 10, would I be more or less certain about my standard deviation versus a sample of 80?
Less.
At 10, I'd be less certain, right? So somehow, if I take a really small sample, this thing really should grow quite a bit. You guys with me on this? Because if I don't know the real population standard deviation, how do I cover for that? I increase my confidence interval a little bit because I don't know what the hell it is. So I've got to get my confidence interval a little bit bigger so I'm still certain that I caught the real thing. So if I took a really small sample, I'm really not sure about my S, right? Because I have a very small sample. So I should have to make this like really big. If I take a much bigger sample, it doesn't have to be that much bigger to cover for something, right? Because the larger of a sample I take, the more certain I am about what I see. So what we do then, and I'm trying to cut to the chase here because this really isn't that big of an idea. The most direct control I have over how wide my confidence interval is the z-score. That's the one thing I can change for any given situation, right? Mm-hmm. So all we do, and this is where people sometimes moan and groan, but it's not that big of a deal. We don't use a z-score. We don't use a z-score chart. We use what's called, I already kind of gave it away earlier, a t-score. So it's just looking up the same idea, look up a score on a different chart now. That's all. Same formula. But now if I know S, I don't know sigma, I know S. What has to go here? T. And I'm sure obviously right now I probably have people going, shit, just getting used to Z. What the hell else we got after that? We got W scores coming up. No, we don't have W scores coming up. I brought a few copies in case somebody came without their book, but if you flip to the very back, there's the Z scores. Take one page from that, there's the T scores. So we put this up here so you can see how this works. Can I do that without waking everybody up? Maybe. Here it comes. That's quick. So one little thing I got to talk about for a second here is Remember a long time ago when we did standard deviation, we had to do the tables? Remember those awesome things? What did we divide the standard deviation by? It was supposed to be an average distance, right? So for a population, we did the sum of the distances squared divided by n. For sample, we divided by n minus 1. And at the time, I tried to explain it a little bit about it was an adjustment because the standard deviation of a sample is always going to be different. I'm trying to adjust for the fact that it's a sample. But it's also known as something else. If I gave you three numbers, if I wanted three numbers, and I wanted the average to be 10. Now, first off, let me see if you guys know this. I think we've talked about this before. If the average of three numbers is 10, what do they have to add up to be?
30.
Because the only thing that makes 10 when you divide it by 3 is 30. You guys with me? If you don't, I don't know a damn thing about any of the numbers. So what could the first number be?
1.
I like it. It could be 1. What could the next number be? 6. But can the last number be anything it wants to be? No. So how much freedom would you say you have? You have three numbers, but you only have freedom over two of them. Because the last dude's the responsible dude. He says, oh shit, guys. You guys did whatever the hell you wanted to. So far, I got 7. What's the last number got to be then? 23. Now, if you try it, these will average to be 10, of course, because we forced them to add to be 30. Divided by 3 is 10. How are we doing so far? So the idea of degrees of freedom, henceforth known as DF. This is way too many letters in this. It's always going to be one less than the total number, right? If I had 8 numbers, I can make the first 7, whatever the hell I wanted to. And the last one's got to be the one to make it come out to the right sum. You guys kind of with me on this? So the little formula for degrees of freedom is n minus 1. Kick ass. Because you'll notice, what's it say on this table? What do you have to know to be able to use the table? Degrees of freedom. Okay. So, another little thing I want to point out, and this table actually is really kick-ass awesome. I want to show you why. When I make a confidence interval, how many tails are there? 2 tails. Do you notice how this breaks it down into 1 tail and 2 tails? So if I wanted 90% confidence interval, what percentage is in 2 tails? 90% confidence, what percentage is in the 2 tails? 10%. What percentage is in 1 tail? 5%. So they both lead you to the same column. Do you see what I'm saying? That's kind of nice. So no matter which way you look at it, you're going to get to the right column. Right?
Say that again.
So if I want a 90% confidence interval, what percentage is in the tails?
It's 10.
Yeah, exactly. So alpha is 0.10, right? That's the amount in the 2 tails.
Right.
So in the 2 tails, there's 10. Okay, what would be in the 1 tail? 0.05. So whichever way you look at it, they both give you the same column. That's cool. Also in chapter 8, we're going to be doing some things called 1-tail test and 2-tail test. And then you just look at the one you want. That's kind of nice. Another really kick-ass thing. This is like one of the only books that doesn't do this. What did we say earlier about the larger my sample gets? Do I have to make my confidence interval so much bigger?
No.
No. So in the event that my sample gets really large, if I take a really big sample, then I can effectively not have to adjust for it then. I can say, well, that's basically the right number then. Right? So notice this. For any situation, notice how the numbers for a sample size of 4. Oh, I'm sorry. That's always nice. Look up here. For a sample size of 4, I would need a score of 4.604, for example. As my sample gets bigger, what happens to the scores I need? And isn't that going to make this error smaller? Which goes along with what we said. The bigger my sample is, the smaller my error should be. And what does it become at the very bottom? Does anybody see what these numbers here, when it's large, what are these numbers here? 1.96, 1.645. We're used to those. 2.575 effectively, but they rounded it to 6 on this one.
9%.
Those are z-scores. So besides large, you can write z. Z-scores are actually on the t-chart. Now watch what little thing this is going to help. And I love some of the looks I get for that. Go ahead. Do what? So these are t-scores. These are always going to be bigger than the z-score you would have used, because it's covering for the fact that you don't know the real standard deviation. It has to make your confidence interval a little bit bigger just to cover for the fact there's something I don't know. Does that part make sense by itself? Right? So if I always think about the scene from Fugitive. It's going back a way. You ever seen the movie Fugitive? And Tommy Lee Jones is like, we have to make a search area of this because of how far he would have traveled. Well, if I'm less sure about how fast Harrison Ford can run, what am I going to do with my search area? Make it bigger. Shit, that's exactly what we're talking about. The confidence interval is sort of like my search area where I'm looking for the real whatever, right? So now when you do your test, you'll be thinking about, it was the one-armed man. So these are z-scores, which really are cool. Can anybody tell me 0.02, what confidence interval would that relate to? Two tails, 0.02, what confidence interval would that be? 98%. Do I have that on the baby chart, 98%? Do I have the z-score? No, but I have it here. The z-score for 98% confidence interval, if I can use z-scores, is 2.326 or 2.33. Which actually should sound familiar. We've done one in the 98% confidence intervals before. So this chart is actually a little better than that baby chart for z-scores. Okay, maybe, yes.
I'm sorry, I'm confused. The z-score you're saying is just the large line or all
Good.
of these?
Large.
Large, okay.
Because again, a t-score will always be bigger than the z-score would have been unless your sample is so damn big that the standard deviation is actually basically the right one, right? So if my population is 5,000 and my sample is 4,900, do you think my standard deviation is really that far off?
No.
Hell no, especially if it's random. If I truly took random sample of 4,900 out of 5,000, I don't have to use a freaking t-score. I can use a z-score. My standard deviation is not that far off, barely far off. I'm almost certain about it. You guys kind of with me? That's what I see here. The larger my sample gets, the smaller my t-score has to be. I don't have to make my confidence interval that much bigger to cover for me because I'm more and more sure about the S that I find. Is it that far off from sigma? No. For a bigger sample, it's getting closer and closer. Right? So let's do a concrete example. I think it's part of what you guys want. You're like, you're talking all this stuff about this, but let's see what this works like. So here's what something might look like for this. You take a sample of 43 students and find X bar. Let's say, let's see, what does this represent? I don't care. X bar is 14.1 and S is 1.89. Okay. So I'm not feeling creative right now. I don't know what these numbers represent. Not shoe size, or else we're looking at big ass feet. So I don't know what I mean. Right here. Now here's the funny thing. I'm not allowing you to put words on your formula sheets. You can't put notes. None of that shit. But you notice how these formulas, which can definitely be on your formula sheet, they tell you when to use a t-score. Use a z-score when I know sigma of standard deviation of the population. Use a t-score when I only have standard deviation of a sample. Can't write notes, but they are notes. So I can't do anything about that. So you got a free note there when you write your formulas down. So here, I only have S. But there was one other thing though. In order to do either T or Z scores, what kind of distribution do I need? Normal. Did I say this is normal anywhere?
No.
Indirectly I did. I didn't say it directly. How did I say it indirectly?
You didn't say anything. The sample of
Oh,
the
sample's
is more
bigger
than
than
30.
Good. Normal n equals 43. It's bigger than 30. Check. 2. Population standard deviation unknown. Must use t-scores. You can only use a z-score if you know the population standard deviation. If you don't, you have to cover your ass by using the larger t-score. Right? I still like this when you guys giggle when I say ass. Okay, so it's going to be the same exact formula. Can somebody help me out? What's the degrees of freedom? Because I can't use that chart until I know the degrees of freedom. Yes, 43 minus 1 is 42. What's my, did I say confidence anywhere? No. Make a 95% confidence interval. So what's my t-score going to be? Well, let's see. I want to look at degrees of freedom. Of course, I chose one that's not on here. That's awesome, Jeff. Anytime that happens, use the one that's right below that. You go below. So we're going to use 40. Okay? We cool with that? 42 is not on the chart. We're going to use 40. Yes, ma'am.
So you don't use the one as closest, doesn't matter. You always go down.
You always go down just to cover yourself. If you round it to the next one, I'm going to be okay with it.
Okay.
But just to be more conservative. If you go the other way, you're actually making your confidence a little smaller than it should be. Let me make it bigger than it should be. Then I'm still certain. Is somebody cool with that? I don't see 42, and then I'm going to use the next one down, 40. Which column am I looking at for a 95% confidence interval? 1, 2, 3, 4, 5. Which column do I want to look at?
The middle one.
Good, the middle one, because if it's 95% confidence, there's 5% and 2 tails. So if I look in the middle column, go down to 40, what t-score do I see? Good, 2.021. Sweet. Did you guys see that?
Why did you go?
So again, let me do this again. I want a 95% confidence interval. What area is in the 2 tails then? So a 95% confidence interval would look like this. What area is in these 2 tails? 5% must be outside, right? 95% inside, 5% outside. So I know I'm looking in this column. How far down do I want to go? 40. Because that's the closest thing below my degrees of freedom. So there's my score I want to use.
Okay, you still lost me.
Okay?
You said in one tail, okay, in the second tail, but what about the first tail?
No.
I mean,
The area in both of these tails is
it's
5%.
right.
If you want to, what's the area in this one tail?
Okay, point two point. Yeah.
Which would be the same column, right?
Gotcha.
So that's what I was saying earlier. It doesn't matter
Yeah.
which way you look
Yeah, I
at
got
it. You got to
I
get to the right
I got
column.
it.
Oh, come here. Sure.
Oh yeah, I wanted to tell you, you might want to put it to cover, because it covers both. Most of the time you have it covering this one, and you don't do nothing on this one.
Don't worry. I'm going to try to put it in the middle there when I can. Right now, I don't want it to freak out with the projection. Where am I at? Okay, so now we can do everything. We got the t-score was 2.021. What z-score would I have used? If I would have known sigma here, 95% confidence would be what z-score?
95%.
1.96. So isn't this a little bit bigger than the one I would have used? Just to cover myself for not knowing the real standard deviation. I got a decent sized sample, not very large, but decent. So it's not crazy bigger than 1.96, but it is a little bit bigger, just to cover my butt. So when I put together this formula, it's going to be the same formula as before, really. My sample mean, give or take a score, either a z or t, in this case a t-score, times the standard deviation that I have divided by the square root of the sample size. It's really the same formula. So what do we find here? 14.1, give or take, 2.021 times 1.89 divided by square root of 43. Be really careful. One big mistake I see is people put 42 there, but you want n there, not degrees of freedom. And now you attack it the same way we did the other confidence intervals. You find the error, you go from there. So first find the error here.
So why did you put 43?
Because what's the sample size? The degrees of freedom was 42, but that chart needs it. The formula needs n. 43 is my sample size. Cool. So what are you guys getting for the error?
5.825.
I get 0.582. So then I would take 14.1 minus 0.582 and 14.1 plus 0.582.
Fourteen six eight two.
So roughly, just rounding off to a couple places. 13.52 to 14.68. So then your statement would be, we are 95% confident that the interval 13.52 to 14.68 contains the true mean whatever. Okay, maybe. Freaky ass shit, I know. Let me give you guys one to try on your own. Take sample of, oh what John? 37 trout and find average filament length of 20 inches, standard deviation of 2.15 inches. How are we doing so far? So here I'm being slightly more evil. Not so evil yet, because you should know you're going to have to use a t-score. But can somebody point out to me what it is here that tells you that? Here it was really obvious because I used the letter S. Ooh. Here is the way you're going to be given it more frequently.
An average.
The average.
Where did my standard deviation come from? Did it come from a population or from a sample? Beautiful. And do you see how we kind of hide that fact? They didn't hide it. We took a sample and we see this and this. So both of these must have come from the sample. So that standard deviation must be a sample standard deviation. I have to use t-scores. That's the process of thinking you have to go through. Because on a test, I'm not going to order them. They're going to be whatever order I want it to be, and then you got to figure out T or Z. Okay. Create the 98% confidence interval for the true mean length of trout. Let's see if this will work here. Bless you.
have extra t-square, please?
Anybody else need a t-score? They're in the back of your book or in that insert. There you go. Oh. So what t-score?
2.434.
Say again, sorry.
2.434.
2.434. So you look at 90%. So I want 0.02 in the two tails, right?
98%.
98%. So I want 0.02 in the two tails. Look down to the degrees of freedom, which is 36, and 2.434. I love it. Cool. Do you guys see how to get that? This is actually a much easier chart to use than the z-score chart, honestly, right? Z-score kind of gets you cross-eyed if you're trying to find something. This is very straightforward. Now I've already forgotten. 2.434. So now I just got to plug and chug. X bar, give or take, t s divided by square root of n. So the mean was 7, give or take this many standard deviations, which will be the old one divided by the square root of the sample size. So start at the mean you found, give or take this many steps, and then you'll be 98% sure that you caught the real average trout length. Yes, ma'am.
You know how you were talking about knowing it was from a sample? How would that question?
They'd have to
say
be,
that-
here's the funny thing, they'd have to be very specific if it's from a population. And it goes back to what I said way earlier in the class. They have to make it very clear that it's a population we're dealing with.
So they would say
Because it's not a
population.
normal situation. Yeah, they'd have to say, and it's known that the population standard deviation, or they have to use the symbol sigma, right? So you know you got a population standard deviation. Otherwise, if they don't say, you have to assume it's a sample. And this one actually tells us directly. We found this stuff from a sample. Cool.
Can I ask you a question?
Yeah.
If it doesn't say it's from a sample, do you assume it's from a sample?
What do you think? Yes. If it doesn't say, what happens normally in statistics is we take a sample. In fact, that's the whole purpose of this. And which would be worse? See if you guys get this. Doing this as if it's from a sample when it's really from a population, or the other way around.
What's the question?
Because if you make it as if it's from a sample, it's going to be bigger, which will only cover your ass more. Whereas if you think it's from a population or a sample, you're going to make it smaller than it should have been. You have a much more likely chance you're wrong then, right? So when in doubt, treat it as if it was from a sample, because you can only make it more conservative anyway. So you're just being more safe. How are we doing so far? Semi-decent. All right. And now here, just get your error.